Okay. It's a question. All right. So today we are going to do the most horrible calculation called ANOVA. Yeah. Okay. Now, ANOVA stands for analysis of variance. When do you use ANOVA? When do you use ANOVA? When do you use it? Three or more population. Okay. So basically, when you are comparing three or more samples. Okay. So because when you're comparing three or more samples of population, essentially the good thing about ANOVA is the null and alternate hypothesis is fixed. Okay. Your null hypothesis is always all means are equal. The alternate hypothesis is at least one mean differs from the rest. Okay. So this hypothesis is always the same for every ANOVA. Just which mean and which mean you're talking about. Now, what does it really explains is null hypothesis means all means are equal. Alternate hypothesis just tells you that at least one mean is differs from the rest. The problem with ANOVA is that it does not tell you if you reject null hypothesis. It actually does not tell you which mean is different. So let's say you have only three samples, A, B, C. If you reject null hypothesis, it doesn't tell you that A differs from B or C, B differs from A and C, or C differs from A and B. It doesn't tell you that. Second, it tells you that at least one mean is different from the rest. It doesn't even tell you whether are there two means that are different. Let's say there are A, B, C, D, E, 5 samples. Reject null hypothesis. It doesn't even tell you that is A differs from the other 4, B differs from the other 4, or is A and C differs from B, D, and E. It doesn't tell you which combination. So you need other tests to do that. Okay. Now, what will happen if you, let's say just now, Matthew say that you need 3 or more samples. What will happen if you do ANOVA for only 2 samples? Can the calculation fail? That means will the calculation give you error? Can the equation still work? That's what I'm trying to ask you. Do you think the equation can still calculate something? Yes, right? So what happens when you do one-way ANOVA for 2 samples? Okay. If you do one-way ANOVA for 2 samples, in fact, during your lab session, you can actually try this. If you do one-way ANOVA for 2 samples, it is actually equivalent to t-test assuming equal variance. It's mathematically the same. When you do one-way ANOVA for 2 samples, basically you come to a conclusion that looks like this. Your F statistic is actually the square of your P statistic. Okay, this is just for a bit of more information, not really a syllabus anyway. Okay, So what on earth we talk about this term called one-way ANOVA? You have one-way ANOVA, your sample, your tutorial actually give you two-way ANOVA as well. So the one in that one-way ANOVA basically refers to one category of your means. So you can have two-way ANOVA, three-way ANOVA, and so on. Okay, there's no limit to what you can do with it. Just that Excel can only do out the two-way ANOVA, and it's very clunky to do two-way ANOVA already. Okay, this is why you have to use R for three-way ANOVA or more. So without further ado, let's go to your tutorial, and we'll do two questions. I'll show you how to do two questions. We'll do two on the board. So let's start with question number 2. Question number 2. Question number 2 tells you that a baker shop, there are 3 ovens, and you are trying to test whether is the average temperature of the 3 ovens the same. Okay. So question 1. So you start off with the table first. You have oven, you have temperature. So oven 1, oven 2, and oven 3. Okay, so let's write out 213, 193, 221, 205, and 194. This is 219, 224, 235, and 251. 189, 238, 241, 233, and 190. Okay. So with that, the null hypothesis is that the average temperature of all ovens are equal. The alternate hypothesis is that the average temperature of at least one oven differs from the others. And here you are testing at 5% significance. Okay, very important, ANOVA doesn't have two-tail test anymore. ANOVA is always one-tail test. Okay. There's no more two-tail test. Now, what you need to do for ANOVA is then to fill up the ANOVA table, which is actually this table. Okay, you have the variations, treatment, error, and total. Okay. Then you have sum of squares, degrees of freedom, in sum of square and your F statistics. The only thing you don't bother is the last three cell. Okay. Now to do that, the first thing you should calculate is the means. So the one in one way ANOVA is actually the carbons. So the first thing you need to calculate is the mean and the variance. Make sure you calculate the variance, not standard deviation. So this you get 205.2, 232.3, 218.2, and the variance is 146.8 and 146.2. Or 200.9, 694.7. Okay. Here you have time, please check your calculation, make sure you get it right. After that, what you need to calculate is this thing called a grand mean. Symbolically, grand mean is the mean of the means, but please do not use the mean of the means. Basically, grand mean, you take, it's actually the average of all values. Okay, do not use the mean of the means. Very risky. Because why? 205.2 come from 5 numbers, 232.3 come from 4 numbers. So you actually have to multiply them up first. Make sense? So in this case, you will get 217.6. Okay, so how to get 217.6? What you really need to do is, you want to get the mean, also get, it's actually 205.2 multiplied by 5 plus 232.3 multiplied by 4 plus 218.2 multiplied by 5. Okay, then the denominator is 5 plus 4 plus 5. You can do that. Okay. The average of the average, the mean of the means, only works if the sample size are equal. Okay, but it's not. Okay. Up to this part, any problem? Okay, so let's do the next one. We will find out what is this number here. The sum of square for treatment, the SST, which is this value here. Okay. Sum of square for treatment is essentially the summation of n, the mean of itself, minus the grand mean squared. Okay, so you take each number to multiply up. Now, which means that expand it out, you have 5, 205.2 minus 232.2. 218.2. And you drop in the grand mean for each one. 217.6, 217.6, 217.6. Okay. Then with that, you get 1635. Okay, then you put 1635 here. So you're done with one. The other component is your sum of square error. So your sum of square error, which is actually this value, is then n summation of n minus 1 multiplied by the variance, not the standard deviation. So here what you have is 5 minus 1 multiplied by 146.2 plus 4 minus 1 multiplied by 200.9 plus 5 minus 1 multiplied by 694.7. Okay. So then you end up with this number 3966. We put in 3966 here. Okay. So indirectly, the mean you actually use in your sum of square treatment. This you use it in sum of square error. Okay. After that, the total sum of square, just add them up. You get 5601. Okay. Now, next step, degrees of freedom for treatment. Your degrees of freedom for treatment is actually the number of samples minus 1. In this case, it's 3 minus 1. So you have 2 here. Okay. But your degrees of freedom for total is actually sample size minus 1. So in this case, 5, 5, 10 plus 4, 14. So here is 13. Then you work backwards because your degrees of freedom for total is actually your degrees of freedom for treatment plus your degrees of freedom for error. So you work backwards, this will be 9. Okay, no. 11. 11. Okay. So far so good. After that, your mean sum of square is the same. Your mean sum of square for treatment is actually your sum of square for treatment divided by degrees of freedom for treatment. And the mean sum of square for error, actually the sum of square for error divided by degrees of freedom for error. So it's 1635 divided by 2, you get 817.5. 3966 divided by 11, you get 360.5. Okay. Finally, you have your F statistic. Your F statistic is then your sum, your mean sum of square for treatment divided by mean sum of square for error. This number divided by this number. So you get 2.268. Once you're up to here, the next thing is to find the critical value. So your critical value, you need your F statistic. Okay. Then the 2 degrees of freedom. One is the degrees of freedom for treatment, degrees of freedom for error. So in this case, it is 0.05, 2, and 11. So you find from the table, you get 3.98. So then, what is the conclusion? Do you accept or reject null hypothesis? Accept or reject null hypothesis? F statistic and the degrees your critical value. Fail to reject or reject? Fail to reject. So you say, since your F statistic is actually less than your F critical value, you fail to reject your null hypothesis. Okay, that's it. Okay, so where are all your marks? Okay, let's try to work out. 1 mark here, 2 mark here, 3 mark here, 4, 5, 6, 7. Okay, you end up with 8, 9, 10, 11 here, 12 here, 13, 14, 15, 16, 17, 18, 19, and finally is 20. 20 marks. Okay, now question. Is it tedious to do? Yes, very tedious to do. No doubt. If I were to mark this question, which is the first number that I will see? Which is the number that I'll check first? Make a guess, make a guess. 1. The number 1. Correct. I'll look for this number first. Okay. Now, where does this number, if this number is wrong, basically I have some idea in my mind what is the range I can accept. If it's like 1 point something, that means wrong already. So work backwards. How do I remove your marks? If this is wrong, automatically one of these are wrong, and usually both are wrong. Then one of these are wrong. If this is wrong, then you can forget that this is wrong, this is wrong, this is wrong, and this is wrong. Okay. Now, if you hit to sum of square error is wrong, the number 1 problem is this is wrong as well. That's how I minus the marks. Okay. So usually, either make sure you get this part right first and check here. Check your grand mean because your grand mean is going to be used in everything. Okay. How can I be a better buster? We'll come to this again. So, how? If you look at all this, right, assuming that everything is right, they get all the marks. How to make you lose marks? How to make sure that you're going to gain marks? Can you guess? Now, how do I get how it can be more evil to make sure that you don't get your marks? Hello, anybody? Quick, give me some idea. Assuming that you are me now. Try. Then how can I be more evil here? Why? You have to know how can I be more evil. Okay, the easiest way that I can be more evil is I try to make these two numbers as close as possible. I try to make these two numbers as close as possible. So if you round off too quickly, all these marks I'll just kill you from here. Last 3 marks here. Since I already know what the degrees of freedom, right? I can play around with your data so that the final result, you get something like 4.05. If you round off too quickly, everything will be wrong in the middle. Easy. Okay. So any question with one-way ANOVA? Yes, it's very tedious, but it's quite doable. So let's go through question 4. So this is one-way ANOVA. Question 4 is two-way ANOVA. Calculation-wise, it's actually the same. One-way ANOVA, you are actually doing 2 sets of, or rather two-way ANOVA, you are actually doing 2 of one-way ANOVA. So let's clean up this mess. The whole board for this. Okay. Question 4, 5. Question 4. Okay, question 4. Is it question 4? Two, 3. Okay, question 4. Now, question 4 asks you to test for different brands and different fatty acid level. So question 4. Now, question 4 itself, you have 2 sets of hypotheses for two-way ANOVA. Essentially, hypothesis 1 asks you for all brands are equal. Alternate hypothesis that at least one brand is not equal. The second hypothesis, basically all different mean of all fatty acids are equal. And the alternate hypothesis, we have two of them. So to do your calculation, you start off with the table. Then you have your low, medium, and high. Okay. Then you have brand A, B, C, and D. Okay, so this is your brand. This is your fatty acid level. We put in 13.6, 12.5, 16.4, 17.2, 14.1, 12.8, 15.8, 18.1, 14.4, 13.4, 17.2, 18.7. So once you have that, there are a few things you can calculate first. One is to calculate the mean and the variance. To calculate from the row wise. So row wise for the mean is 1403, variance is 0.163. That is 12.90, 0.210, 16.8, 0.160, here 18.0, 0.571. Okay. So basically this you calculate this position of the row. Okay. So that's one. The second, this is one way Anova is what you did just now. So let's construct our table. Okay. Variation. Your variation is your fatty acid. Okay, then you have your sum of square, degrees of freedom, mean sum of square, and your statistic. After which you can calculate for the grand mean as well. So the average of these numbers. So the grand mean is 15.4333. Now, then you do the next part. What happened is you do the second column. Now, here you have the mean and variance as well. So you calculate downwards by column. That's the second factor. So you have 14.925, 4.996, 15.45, 5.897, 15.925, 6.009. So then the second factor is actually the brand. Then you have error and total. Similarly, the three items that you don't have to calculate will be this three. So let's look at your degrees of freedom first. Now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 12 of them. So total degrees of freedom is 11. Okay. Fatty acid, how many degrees of freedom are there? There are 3 levels, so degrees of freedom is 2. For brands, there are 4 brands, so degrees of freedom is 3. Then you just add up, look at what is the degrees of freedom for error, which is 6. Okay, just reverse calculate everything. So now what you have is 2 sum of squares. So you go back to your formula sheet, find out the 2 sum of squares. So you have one for, where's my black marker? Have sum of square for fatty acid. Actually the same calculation, just that a lot more tedious. So now is for fatty acid. You just work everything out. For fatty acid, the sample is 3. 3 times 14.925 minus 15.4333 square plus 3. This one is 15.45 minus and still 3. So you end up with 15.925. Okay, just do one set first. And for that, it gives you, for fatty acid level, sum of square is 2.0018. So 2.0018 divided by 2, you end up with 1.0009. Next, you do for the brand. So sum of square for brand. Okay. Sum of square for brand is 4. Sorry, this is 4. 4, 4, 4. The sum of squares for brand, because there's only 3 of them, so it's 3. And you have 14.03 minus 15.4333 squared plus 3, 12.90. Okay. So then you end up here is 50.5281. If you divide that by 3, get 16.8427. Okay. Now then sum of square error, you can do either side. Actually doesn't really make much of a difference. Okay. Sum of square error, you can do either side. So sum of square errors, you end up with 0.1769. Okay. You use the sum of square error on the fatty acid, or use the sum of square error if you use from the brand itself, it will give you a slightly different answer, but it's close enough. It doesn't make much of a difference. Then after that, you just add up these two numbers. So here I will give you 52.7068. And you divide by 6. Because this number depends on which axis you are doing. Sum of square error you are doing for the brand or for fatty acid, the answer is going to be slightly different. But because it's going to be divided by a bigger number, so it actually doesn't make much of a difference anymore. 0.2948. Then what you have here is you just take the mean sum of square divided by the error. 1.0009 divided by 0.02948. Here is 16.8427 divided by 0.02948. So here you get 571.33, and here is 33.95. Because of this, you end up with two critical values. Okay, hopefully you can see. So let's write here. For your hypothesis 1. Okay. Critical value is 0.05. Hypothesis 1 is the brand. So brand is 3 and 11. 3 and 6. Okay, so for 3 and 6, it is 4.76. Okay. Now for your hypothesis 2, and 6. That gives you 5.14. So in both cases, you reject the null hypothesis. So in this case, say that since your F is more than your F critical, you reject your null hypothesis. Means you accept alternate hypothesis. Okay, so for therefore the mean of here you just repeat the same thing. Okay, that is basically your entire question. Sounds good? So okay to do your two-way ANOVA for your test? It is tedious, but it's doable. Okay, most of the time you make careless mistakes. All right. So with this, we're going to have some questions to do. Okay, we want to do question 2 and question 5. So who would like to do question 2 and question 5? Question 2 is one way, question 5 is two-way. Five. Okay. Okay, so let's try it. In everything. Let's do one at a time. Okay, Marcus, do question 5. So you're going to use 2/3 of this board. That's not right. Okay, 1, 2, right. Just like see 2/3 around here. Okay, good. Question 5. Okay, question 2. Who have I not called so far? Anyone have I not called? Anyone like to do? Who have I not called so far? Ethan, you done already? Huh? Let's see, question 2. Question 2. Question 2. Let's see, the Statistic what? Yeah, right. So you're fine. You know, question 2 we did already. So question 3. Question 3. Okay, question 3. What is your? You didn't do question 3. Oh. Okay, please do question 3. No, what? Who has done question 3? Anyone? Anyone here? Question 3. Question 3. Question 3. Question 3. Question 3. Okay. Question 3. Okay, draw the ANOVA table first. Why is important? Where else? High and fertilizer. Fertilizer and what is it? Medium high.
Right on Nivea. What's the thing up? Boy.
then you write either reject or accept null hypothesis here. Okay. All right. Correct.
Something I failed. Give me a sec.
Question 3. Correct. After you got it right. This is correct. Correct. So everything is correct. Reject null hypothesis. Okay. Okay, question 3 is right. Okay, question 5. Question 5. Question 5 numerically is also right. Let's get a look at this number first. This 2 is correct. Set. So there's a difference between fertilizer use. Okay, Marcus, one thing, when you write this, don't write it this way. If you want to write this way, make sure you bracket it up. Okay. Otherwise, it's mathematically wrong. Okay. Okay, so for question 6. Okay, question 6, part 1. After doing all the calculation, explain why should the student do one-way ANOVA test first. What's the reason? Answer. Question 6.1. Part A. Yeah, because 3 samples. Okay. What are the assumptions for one-way ANOVA? There's actually 3 assumptions. One is independence. That means the data must be randomly collected for all 3 of them. Normality. Each of the data set, that means for each of the samples, must be normally distributed. The third one, just now we've alluded to it, is the homogeneity of variance. That means all 3 of them have to have the same variance. Okay. Remember, if you do one-way ANOVA for 2 samples, it's equivalent to t-test assuming equal variance. So actually ANOVA assumes equal variance. Unequal variance is not called ANOVA anyway. All right. So what is the mistake? The mistake is actually in the alternate hypothesis. Okay, it's not mu1 more than mu2 more than mu3. Okay. So that's it. Tutorial question 1 is false, and the rest is true. False, true. Okay, very important. Your F statistic cannot be negative. You can never be negative to begin with. It's a quotient. Okay. Okay, so any problems so far? Okay, let's stop this recording.